In this problem, we're going to talk about the concept of half-life. So, remember in this type of problems when we were talking about a problem that doubles its original amount, what the problem tells us is that after a certain amount of time, the mass has an augmentation of mass. In this case, it's double. So what we did is that after a certain amount of time, we have doubled the amount of the original amount of mass that we had. Okay, remember, if this was triple instead of double, we would have 3 times the amount of the original mass, etc. So when we're working with half-lives, we're talking about after a certain amount of time, we're going to have half of the original amount. So what this problem is telling me is that after 9.45 minutes, I have 1/2 of the original amount of magnesium 27. Notice that it is not specifying an amount for magnesium, meaning that we can think of the original amount as 1. If I have 1 gram of magnesium, after 9.45 minutes, I will have half of it. Why? Because we're talking about half-lives. So I'm being asked what is the decay rate for magnesium. So to do that, I'm going to plug the information as usual. I know what I want. The original, I want the half of the amount of the original amount to happen when? After 9.45 minutes. So I want to find the rate. Notice that this is a decay rate, meaning that that at the moment that I solve for r in this equation, that value is going to be negative. I don't have to put a negative sign here, because in the moment I plug my final result into the calculator, that is actually going to give me a negative value, okay? So because I want the negative, to find the rate of decay, I'm gonna solve this exponential equation as usual. So this is 1/2 over 1, that is exactly the same, equals E times r to the power of 9.45. Now I can rewrite this as an exponential equation or apply a logarithm on both sides of my equation. So this is natural logarithm of 1/2 equals 9.45 r of ln of e. By now we know that this is 1. So natural logarithm of 1/2 over 9.45 equals r. So this is my rate of decay. If we plug this into a calculator, you're going to find that this is actually negative. So it is actually the decay rate because it is negative. So let's write the final model. The model is going to look like this. The mass of magnesium at certain time is my initial data, that is just 1, raised to the power of e of my rate of growth, or my rate of decay, times my variable, that is t. Now, if I want to know when will I have 1/5 of magnesium 27 of the original amount, what am I being asked? I'm being asked about time. When I have 1/5 of the original amount. So I'm going to plug the amount I'm being given into the model. Notice that 1 times e is just e. So this is ln of 1/2 over 9.45 t. And I want to solve for t because why? I'm being asked when. That is, I'm being asked about time. So I'm going to solve for t. So I'm going to, the exponential term is already isolated, so I'm going to apply logarithms on both sides of the equation. So on this side, this is ln of 1/5 equals, I'm going to pull the exponent down. Again, this is an ugly looking exponent, but it's still an exponent, so I can pull it down. It doesn't matter if the exponent has a logarithm inside it. Okay? Of ln of v. This is, as usual, this is going to be 1. So this is natural logarithm of 1/5 equals, this is the ln of 1/2 of 9.45 times t. So I'm going to pass that coefficient dividing to the other side. So this is natural logarithm of 1/5 over natural logarithm of 1/2 over 9.45. And this is the value of t. So we will have a fifth of the original amount when t equals this ugly looking number. I can even simplify this more and apply a sandwich law. So this is going to be 9.45 times this. You can check it by yourself.